Section 7.3, Service Discovery and Load Balancing. We've talked about pods and deployments, so let's dig into services a bit. You've got the catalog service application running as a pod in your local Kubernetes cluster, but there are still unanswered questions. How can it interact with the PostgreSQL pod running in the cluster? How does it know where to find it? How can you expose a Spring Boot application to be used by other pods in the cluster? How can you expose it outside the cluster? This section will answer those questions by introducing two important aspects of cloud-native systems: service discovery and load balancing. I'll present the two main patterns available to implement them when working with Spring applications: client-side and server-side. Then you'll apply the latter approach, which is conveniently offered natively by Kubernetes through service objects, meaning you don't have to change anything in your code to support it, unlike the client-side option. Finally, you'll learn how the communication between the catalog service pod and the PostgreSQL pod happens, and you'll expose the catalog service application as a network service. Section 7.3.1, Understanding Service Discovery and Load Balancing. When one service needs to communicate with another, it must be provided with information about where to find it, such as an IP address or a DNS name. Let's consider two applications, Alpha App and Beta App. Figure 7.6 shows how the communication between the two would happen if there were only one Beta App instance.
Figure 7.6. If there were only one Beta App instance, the inter-process communication between Alpha App and Beta App would be based on a DNS name resolving to the IP address of Beta App.
In the scenario illustrated in Figure 7.6, we say that Alpha App is upstream and Beta App is downstream. Furthermore, Beta App is a backing service with respect to Alpha App. There's only one instance of Beta App running, so the DNS name gets resolved to its IP address. In the cloud, you'll probably want to have multiple instances of a service running, and each service instance will have its own IP address. Unlike physical machines or long-running virtual machines, a service instance will not live long in the cloud. Application instances are disposable. They can be removed or replaced for different reasons, such as when they are not responsive anymore. You can even enable the auto-scaling feature to automatically scale your application in and out, depending on the workload. Using IP addresses for inter-process communication in the cloud is not an option. To overcome that issue, you might consider using DNS records, relying on a round-robin name resolution pointing to one of the IP addresses assigned to the replicas. Knowing the host name, you can reach the backing service even if one of the IP addresses changes, because the DNS server would be updated with the new ones. However, this approach is not the best fit for cloud environments because the topology changes too often. Some DNS implementations cache the results of name lookups even after they should have expired. Similarly, some applications cache DNS lookup responses for too long. Either way, there's a high chance of using a hostname IP address resolution that is no longer valid. Service discovery in cloud environments requires a different solution. First, we need to keep track of all the service instances running and store that information in a service registry. Whenever a new instance is created, an entry should be added to the registry. When it's shut down, it should be removed accordingly. The registry recognizes that multiple instances of the same application can be up and running. When an application needs to call a backing service, it performs a lookup in the registry to determine which IP address to contact. If multiple instances are available, a load balancing strategy is applied to distribute the workload across them. We distinguish between client-side and server-side service discovery depending on where the problem is solved. Let's take a look at both options. Section 7.3.2, Client-Side Service Discovery and Load Balancing. Client-side service discovery requires applications to register themselves with a service registry upon startup and unregister when shutting down. Whenever they need to call a backing service, they ask the service registry for an IP address. If multiple instances are available, the registry will return the list of IP addresses. The application will choose one of them, depending on a load balancing strategy defined by the application itself. Figure 7.7 shows how that works.
Figure 7.7. The inter-process communication between Alpha App and Beta App is based on the IP address of the specific instance to call. chosen from a list of IP addresses returned upon lookup in the service registry.
The Spring Cloud project offers a few options for adding client-side service discovery to your Spring applications. One of the popular choices is Spring Cloud Netflix Eureka, which wraps the Eureka service registry developed by Netflix. Alternatives are Spring Cloud Console, Spring Cloud Zookeeper Discovery, and Spring Cloud Alibaba Nakos. Besides managing a service registry explicitly, you'll also need to add the correct integration to all your applications. For each of the previously mentioned options, Spring Cloud provides a client library you can add to your Spring application so it can use the service registry with minimal effort. Finally, Spring Cloud Load Balancer can be used for client-side load balancing, which is the preferred choice over Spring Cloud Netflix Ribbon, no longer maintained. All those libraries offered by Spring Cloud contributed to making it an excellent choice for building cloud-native applications and implementing microservices architectures. A benefit of such a solution is that your applications have complete control over the load balancing strategy. Suppose you need to implement patterns like hedging, sending the same request to multiple instances to increase the chance one responds correctly within a specific time limit. Client Service Discovery can help you with that. A drawback is that Client Service Discovery assigns more responsibility to developers. If your system includes applications built using different languages and frameworks, you'll need to handle the client part of each of them in different ways. Also, it results in one more service to deploy and maintain, the service registry, unless you use past solutions like Azure Spring Apps or VMware Tanzu Application Service, which provide it for you. Server-side discovery solutions solve these issues at the expense of fine-grained control in the application. Let's see how. Section 7.3.3. Server-side service discovery and load balancing. Server-side service discovery solutions move a lot of responsibility to the deployment platform so that developers can focus on the business logic and rely on the platform to provide all the necessary functionality for service discovery and load balancing. Such solutions automatically register and deregister application instances and rely on a load balancer component to route any incoming requests to one of the available instances according to a specific strategy. In this case, the application doesn't need to interact with the service registry, which is updated and managed by the platform. Figure 7.8 shows how that works.
Figure 7.8. The interprocess communication between Alpha App and Beta App is based on a DNS name that gets resolved to one of the instance IP addresses by a load balancer component. The service registration process is handled by the platform transparently.
The Kubernetes implementation of this service discovery pattern is based on service objects. A service is an abstract way to expose an application running on a set of pods as a network service. See this link. A service object is an abstraction targeting a set of pods, typically using labels, and defining the access policy. When an application needs to contact a pod exposed by a service object, it can use the service name instead of calling the pod directly. That's what you did to let the catalog service application interact with the PostgreSQL instance. Polar Postgres was the name of the service exposing the PostgreSQL pod. The service name is then resolved to the IP address of the service itself by a local DNS server running in the Kubernetes control plane. Note: the IP address assigned to a service is fixed for its lifetime. Therefore, the DNS resolution of a service name doesn't change as often as it would with application instances. After resolving the service name to its IP address, Kubernetes relies on a proxy, called kubeproxy, which intercepts the connection to the service object and forwards the request to one of the pods targeted by the service. The proxy knows all the replicas available and adopts a load balancing strategy depending on the type of service and the proxy configuration. There is no DNS resolution involved in this step, solving the problems I mentioned earlier. The service discovery implementation adopted by Kubernetes is shown in Figure 7.9.
Figure 7.9. In Kubernetes, the interprocess communication between Alpha App and Beta App happens through a service object. Any request arriving at the service is intercepted by a proxy that forwards it to one of the replicas targeted by the service based on a specific load balancing strategy.
This solution is transparent to your Spring Boot applications. Unlike options like Spring Cloud Netflix Eureka, you get service discovery and load balancing out of the box in Kubernetes, without requiring any change to your code. That's why it's the preferred option when you use a Kubernetes-based platform to deploy your applications. Service Discovery and Spring Cloud Kubernetes. If you need to migrate existing applications that use one of the client-side service discovery options I mentioned in the previous section, you can use Spring Cloud Kubernetes to make the transition smoother. You can keep your existing service discovery and load balancing logic in your application. However, instead of solutions like Spring Cloud Netflix Eureka, you can use the Spring Cloud Kubernetes Discovery Server for service registry. This can be a convenient way to migrate applications to Kubernetes without changing too much in your application code. For more information, refer to the project documentation. See this link. Unless what you're doing requires specific handling of service instances and load balancing in your applications, my recommendation is to migrate over time to using the native service discovery functionality offered by Kubernetes, aiming at removing infrastructural concerns from your applications. With this general understanding of how service discovery and load balancing are implemented in Kubernetes, let's look at how we can define a service to expose a Spring Boot application. Section 7.3.4. Exposing Spring Boot applications with Kubernetes services. As you learned in the previous section, Kubernetes services let you expose a set of pods via an interface that other applications can call without knowing the details about the individual pod instances. This model provides applications with transparent service discovery and load balancing functionality. First of all, there are different types of services depending on which access policy you want to enforce for the application. The default and most common type is called cluster IP, and it exposes a set of pods to the cluster. This is what makes it possible for pods to communicate with each other, for example, catalog service and PostgreSQL. 4 pieces of information characterize a cluster IP service. The selector label used to match all the pods that should be targeted and exposed by the service. The network protocol used by the service. The port on which the service is listening. We're going to use port 80 for all our application services. The target port, which is the port exposed by the targeted pods to which the service will forward requests. Figure 7.10 shows the relationship between a cluster IP service and a set of target pods running applications exposed on port 8080. The name of the service must be a valid DNS name, since it will be used by other pods as a host name to access the targeted pods.
Figure 7.10. A cluster IP service exposes a set of pods to the network inside the cluster.
Defining a service manifest with YAML. Let's see how we can define a manifest for a service object to expose the catalog service application through the DNS name catalog service and port 80. Open the catalog service/K8s folder you created earlier and add a new service.yml file.
Listing 7.3. Service manifest for the catalog service application.
Creating a service object from a manifest. You can apply a service manifest as you did for deployments. Open a terminal window, navigate to your catalog service root folder, catalog service, and run the following command.
See this code?
The command will be processed by the Kubernetes control plane, which will create and maintain the service object in the cluster. You can verify the result with the following command.
See this code?
Since it's of type cluster IP, the service makes it possible for other pods within the cluster to communicate with the catalog service application, either using its IP address, called the cluster IP, or through its name. That will be useful for the applications you'll build in the next chapters. But what about us? How can we expose the application outside the cluster to test it? For now, we'll rely on the port forwarding feature offered by Kubernetes to expose an object, in this case a service, to a local machine. You did that already in Chapter 2, so the command should look familiar.
See this code.
You can finally call the application from localhost on port 9001, and all requests will be forwarded to the service object and ultimately to the catalog service pod. Try visiting localhost 9001 from your browser to see the welcome message, or localhost 9001 books to browse the books available in the catalog. Tip: the process started by the kubectl port forward command will keep running until you explicitly stop it with Ctrl-C. Until then, you'll need to open another terminal window if you want to run CLI commands. Figure 7.11 illustrates how the communication works between your computer, catalog service, and PostgreSQL.
Figure 7.11. The catalog service application is exposed to your local machine through port forwarding. Both catalog service and PostgreSQL are exposed to the inside of the cluster through the cluster local hostname, IP address, and port assigned to the service objects.
So far, we've been working with only one instance of catalog service, but we can take advantage of Kubernetes and scale it out. The following section will cover how to scale Spring Boot applications and address aspects such as fast startup and graceful shutdown, which are essential for cloud-native applications. Note: imagine running all those commands every time you change something in your application and you want to test it locally. It doesn't look very appealing, does it? Don't worry. In section 7.5, I'll show you how to set up a local Kubernetes development workflow to automate all those operations.